Okay, so we'll start a new topic today. As you can see, we're going to generalize the concept of finding either the maxima minima that you know from functions of a single variable or functions of two variables. So that's the whole idea. And we will use the partial derivatives that we have talked about before. So before we proceed with that, I have to make a definition, which is related to relative extrema. And so we say that the function of two variables, f of x and y, is said to have a relative maximum at the point a comma b in the domain of f if f evaluated at that point is greater or equal than f of xy for all points x comma y in a circular disk centered at a comma b. So this is a generalization of what it means to be a local maximum in one dimension versus a 2D domain. Clearly, well, when you do calculus, you perform derivatives which are helpful to find local linear approximations. That's how we will use this kind of criteria, and that's how or why the definition relates to relative extrema, meaning like local minimum or local maximum. In this case, what you have is basically a local maximum because it's the maximum over the points close enough to a comma b. That's why you define a disk. So what you can guarantee is that in a certain neighborhood, which is defined by that disk, the value at ab is greater than any other value taken at any other point in the disk. That's pretty much it. So the equivalent definition for a local minimum or relative minimum is the following. If you have the following condition, f at a point c comma d less or equal than f at x comma y for all points x comma y in a circular disk centered at the point c comma d, then f of xy has a relative minimum at the point c comma d. Again, the character of this minimum is local, that's why we call it relative. And you define the neighborhood over which the value is less or equal than any other value taken at the disk. So this is the 2D extension. You want to remember what we used to do in the 1D case or in single variables. We related local maxima or minima to critical points related to the derivatives. In this case, we will do something similar, but we will have to use the partial derivatives, which is what we will do. But before that, we have to define what is a critical point in the 2D case. In the 1D case, it's the set of points at which the derivative vanishes. We will have a similar definition, which we have to make. So this is the following. So if we want to define what is a critical point of the function f, we talk about the points a comma b in the domain of the function of two variables f of xy, for which both the partial with respect to x of f at that point is equal to 0, and the partial with respect to y at that point is equal to 0. So in the 2D case, the two partial derivatives fx and fy have to vanish. In 1D, you would only have one variable to take the derivative against, so you have derivative of f with respect to x. Here you need both partials to vanish. That is the concept. Look, unfortunately, the course goes in a rush, which gives you all the essential material for your discipline, and in a way, 2 semesters in one. There's a reason for this if you think about these slopes, because as we saw before, basically these slopes are when you make intersections of the surface with a given plane, it's the slope of the curve at that point. What those partials are useful in general is to define a plane that approximates the function or the surface at a point. So the fact that those two partials would be 0 would be equivalent to the fact that the approximating plane is a horizontal plane, because both this slope and the orthogonal will be 0. So that's a horizontal plane. And that means if you think about the surface, that's basically when you have a minimum. You have a tangent plane that is horizontal. So it's kind of intuitive that you will get, at the minimum, a plane that is horizontal, okay, because it's the minimum. So in any case, I'm just trying to provide some intuition into why the critical points will be related to relative either maxima or minima. And we will see equivalent criteria to the ones that you have in 1D. So we'll proceed. If the function of two variables has a relative maximum at the point A, B, the curve obtained by intersecting the surface Z equal f of x and y with the vertical plane y equal to b has a relative maximum when x is equal to a. So I think in this case it's helpful to do a figure which goes like this. So we have our space, x, y, z. You will do the intersection with a vertical plane, let's say y equal b. So this is the plane. It's parallel to the xy plane and it has a value y equal to b. And, well, you're choosing that because the point is located at coordinates a comma b. And you already know that the function has a maximum, relative maximum at that point. So we're going to draw the surface now and then draw the intersection of that surface with the plane. So you would have something along the lines of this. I'm trying to be systematic in the way I draw this so that the figure looks kind of better. So first, I know that the maximum would be here, for example. And then, if I make the intersection of the surface, which I just drew, with the plane, you would get something like this. Remember, you had the intersection of the surface with the plane. That will give you a curve, which is what I represented here. And then, this is basically a 1D object. So surface intersected with the plane y equal to b gives me this. Then let's say that I evaluate the slope. But the point is that by making that intersection, the curve is a function of a single variable, which is x, because y is fixed and it has the value b. And for curves, for functions of a single variable, I know the story. I know that if I have a relative maximum, if there is a relative maximum for the surface, then of course it is of the curve, because the curve is a subset of the surface, then the slope must be horizontal. So all this show is basically to say that here you would have a horizontal tangent. And of course the coordinates of the point in the 3D space are A, B, and f of A, comma B. And this is just the surface, Z equal f of xy. And to state that for y equal to b, the slope of the curve obtained, which is represented by the partial, because when you take the partial with respect to x, y is fixed, which is precisely the geometrical representation. At that point, the slope would be 0. So, what this way of teaching is trying to do is to relate the 2D case to the 1D case, and using the things that you know for the 1D case, conclude that the slope has to be horizontal. So, you can see the story of why the critical points related to the partial derivatives will be related to the relative maximum. We're decomposing the problem from 2D to 2 problems in 1D. And in this case, what you would have is a horizontal tangent line, as we have made clear from the geometry. And in that case, the slope f of x at AB would be 0 for this horizontal tangent. Now, the picture for the other case would be actually easier because, well, the front plane is the YZ plane, so that might be more intuitive. And we're going to draw the picture. So, in that case, you have x, y, z. Again, you will have the point with coordinates a and b. Let's say that a is here. Something like this. So this is where my point would be. Now I'm going to focus on the plane x equal to a. Clearly, the plane x equal to a is over here. Because I'm choosing the set of points for which the coordinates, no matter what y and z are, always have the x coordinate equal to a. So, if I do the same representation of the surface, which would be something like this, and if I draw the intersection of this surface with this plane, since it's the front plane, I would get a parabola, something like a parabola in this fashion. And I know that the maximum is located here. So it's easier to see the picture now because it's basically in the 2D plane. And again, for this kind of curves in 2D, we know the story. Having done the intersection of the surface with the plane x equal to a, we get a curve which is a function of one variable, which is y, because x is fixed and it has the value a. And since it has a relative maximum by assumption, the slope should be horizontal. So at the point a, b, f of a, b, if you draw for this curve the tangent, you would have a horizontal tangent for which the slope would also be 0. So for values of x equal to a, doing the intersection, blah, 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 etc., the slope of the curve where you have the function of a variable y with fixed x equal to a, which is fy, evaluated at ab, that would be 0, because that's where the relative maximum is located in this case. So think about it. We decompose the problem into 1D problems. The nice thing about calculus is that for smooth functions, well-behaved functions, you can do that kind of thinking in any direction. That is just an extra that I brought to you. But in terms of how we think it, we drew the intersection of the surface with 2 planes. We got a function of a single variable, and we apply the criteria that we know from functions of a single variable, which is that the derivatives or the slope should be 0. So now we know the condition that critical points should satisfy. The theory is more complicated. You have to prove many things, but this is in a way a crash course on calculus. I'm trying to provide some geometrical intuition into what is necessary, okay? So if you have some intuition into why it's happening, the goal is accomplished, I would say. So the second statement is basically that, likewise, the curve formed by the intersection of the surface z equal to f of xy with the plane x equal to a has a relative maximum and y is equal to b, and so the partial of f with respect to y at that point is equal to 0. Basically just stating again this. So the conclusion, if you remember the definition of critical point in 2D, or for functions of two variables, is that the partial derivatives, both fx and fy, vanish, which is what we're seeing. So basically, the conclusion from the geometrical intuition is that if you have a relative maximum, it must be a critical point. That is the way the argumentation goes. The reverse doesn't necessarily follow. If you have a critical point, it's not necessarily a relative maximum or relative minimum. That actually should be clear from, well, even from 1D problems, because you can find functions of single variables for which you have a critical point, and yet it is not either a local maximum or a local minimum. So in 2D, why would you expect the converse to happen, right? So the only observation is basically that a point at which a function of two variables has a relative, say, maximum must be a critical point, because both partials vanish. Of course, if I basically flip this little parabola, the argument would be the same. So the argument that I did for maximum would apply to relative minimum. Just imagine, I flip it, argumentation done. Okay? So when you have relative extrema, the plural in Latin, so the singular is extremo. Extrema means that you can have either a maximum or a minimum. In both cases, you would have a critical point. So we will make a statement indicating this relation, which is the following. And well, if you want, in the meantime, I could show a picture if it helps you. Just wait 1 second. Well, I mean, this is the plot of basically what it means to be a relative maximum or relative minimum. It's just intuitive. The value here is higher locally. Over here, this is the same cut, of course, in a more professional fashion than the drawing that I did, where we do the cut with some planes. This is the plane y equal b, this is the plane x equal a, intersecting, and you get the argumentation of the slopes. So this is just a pretty picture. Now we will make the statement of this connection. Between critical points and relative extrema. So a point A comma B in the domain of f of xy, for which the partial derivatives fx and fy both exist. So let's assume that they exist. Now, it will be called a critical point of f if both the partial with respect to x of f at that point AB is equal to 0, and partial with respect to y at the point AB is equal to 0. So that's just an iteration of the definition that we did before. However, the relation is this. If the first order partial derivatives of f exist at all points in some region R in the xy plane, then the relative extrema, meaning both possibly maximum or minimum, of f in R can occur only at critical points, which is basically writing what we concluded by geometry. And again, if you want, well, the argumentation was basically to reduce from 2D to 1D. In terms of surfaces, you can think that you approximate functions with a plane. If you have a minimum, it's kind of intuitive that for a minimum the plane should be horizontal, because, well, the values would be above for neighboring points. If you would have a horizontal plane doing the intersections, you would have that the slopes are 0 for both cases. And in that case, you conclude the critical points. Unfortunately, we will not extend too much in this notion of the plane, but I think it's useful if you want to imagine geometrically what happens with the surfaces and the derivatives. Now, the note that I had mentioned before is that not every critical point corresponds to a relative extremum. So of course, relative extremum, either maximum or minima, implies critical point. But critical point does not imply maximum or minimum. Okay? The argumentation goes only on one way. And again, you can think of counterexamples in 1D. We will also see an example that is basically proper from 2D, which is the saddle point. And if you have ever ridden a horse with a saddle, if you imagine the figure, you can see that basically if you make cuts in a plane, you get an upgoing parabola, but in the orthogonal plane, you would get a downward parabola. So that is the spirit of the following function. If you have the function f of xy equal to y squared minus x squared, so this points out to the fact that I had mentioned. Because basically if you think what happens if you keep x constant or y constant, you have parabolas either going up or going down regarding on which variable you keep fixed. So just keep that in mind. In that case, for the partial with respect to x, at this point what you would have, well, this is constant, so this is regarded, so this is minus 2x, right? Then for this function, partial with respect to y, you have 2y. Try to imagine it a little bit before we draw the picture. So for this, look, well, we kind of see that if we want to find critical points, which would mean that these two would vanish, partial with respect to x and partial with respect to y, the only possible conclusion is that x should be 0 and that y should be 0, which means that the only critical point could be at the origin. Okay? So I haven't drawn the picture. Formally speaking, we don't know how it looks like, but if I tell you find the critical points, the only critical point will be the origin. So, well, basically, if you want 0 fx implies x equal to 0, 0 equal to fy implies y equal to 0, which means that the critical point is the origin. And it's the only one. By definition. So, again, think of these two parabolas, and then we will make another fact, which is that the surface, which is said equal to y squared minus x squared, has horizontal tangents at the origin along the x and the y-axis. Actually, before we make a calculation, we can see that because when we stay in one of the axes, we make the other component constant. So, for example, let's say that I make x constant, right? So the dependence would be actually here. Let's make it, for example, x equal to 0, which we will need because of the critical point. So in that case, you will have z equal to y squared, which is a parabola going up. Let's think making y equal to 0, you have z equal to minus x squared, so the parabola is going down. So now you see that something fishy might be going on, okay? How can we reconcile the notion of having a maximum or a minima, since in one direction it goes up and in the other it goes down? It's weird, right? So precisely when y is equal to 0, which means that you are in the xz plane, z is equal to minus x squared, which is a relative maximum at x equal to 0. The parabola goes down. So when x is equal to 0, which means that you are in the yz plane, that means that z is equal to y squared. And then you have a relative minimum at y equal to 0. And if you want to draw the figure, well, this is the parabola going down, this is the parabola going up. Of course, in different axes, right? So, as I had mentioned before, the surface z equal to y squared minus x squared is shaped like a saddle. And I'm pretty sure you have seen a saddle before, but I don't know if you had made the observation that it has basically two orthogonal directions in which you either go up or you go down, depending on the direction. So, well, let's focus first, for example, on this one, right, on the yz plane. Z is equal to y squared, so that means that I have a parabola going up. So I would draw a picture like this. Okay, something like this, right? Now, let's make the other cut, right? Y equal to 0, which means I'm in the xz plane. Z is equal to minus x squared. And I think this will help you to imagine this. So, in that case, let's say along that plane, if you want for clarity I can draw this. Along that plane you would have the parabola going down. Okay? So far so good? Can you imagine? Just do the cuts for the moment. And in 1 second we will do the intuition in 3D. By this line of thinking, basically the way to generate the surface, even if you were to do this by a code, would be to take constant values, for example, of y, and draw the surface. This is interpreted as a constant. It's basically add the constant and put the parabola going down, because it's set a constant, which is y squared, and then minus x squared, but the parabola is going down. So you could do something like this, for example. And you could do something like this. Okay? So hopefully, by now you can imagine how the saddle looks like in the horse, right? Basically imagine how you make the parabolas going down with this constant of y squared, which diminishes as you get close to the origin, and then you make them go up. So it's clear how am I generating this, right? But if I make the cuts, of course, in the yz plane, the parabola is going up. In the xz plane, the parabola is going down, and then I generate the whole surface by pushing down that parabola and then playing it back again. Okay? So, but the important thing, I mean, clearly, you do not have either a local maximum or a local minimum, because depending on the direction, either you go up and you go down. That is not what a local maximum should do, or local minimum, regardless. So, I mean, I'm just going to draw this if it helps you, and hopefully it will. Okay? If it completes the picture. If it's still not completely clear what's going on, I might draw show this, if it helps you. And yeah, well, it would be this, right? But again, the figure is doing precisely that. In one direction, the parabola is going down. In the orthogonal, the parabola is going up. Then you generate the surface. I like more the fact that you can basically change the height of the parabola going down, and then you do the whole picture. But if you were to do this in a course of analytic geometry, actually that's the way that you would draw it. And of course, well, this is a very typical example of a kind of surface, which is, of course, called a saddle surface. So this is a saddle surface of the form z equal to y squared minus x squared. And, well, something that I think it's intuitively obvious is to mention that for a critical point, to correspond to a relative extremum, the same extreme behavior either maximum or minimum must occur in all directions, which is precisely the problem with the saddle, because in one direction it grows and in the other it decreases. Yeah, and one last comment is that any critical point where there is a relative maximum in one direction and a relative minimum in another direction is called a saddle point. Like in the example, right? I mean, in this case, the directions were orthogonal. They are not necessarily orthogonal as long as they are linearly independent. You could deform a little bit the picture by basically tilting the x-axis, for example, and the same phenomena would happen. But okay, this is the first basic example of how a saddle surface looks like, which is very intuitive by making this composition into parabolas going up and down and then fixing one coordinate as constant. So hopefully the introduction to the saddle surfaces was intuitive and nice. And then we will do one criteria, which is analogous of the second derivative test in 1D. But now we have to apply partial derivatives because we are dealing with functions of two variables. So we'll study the second partials test. And it's helpful to determine if a critical point is a relative maximum, a relative minimum, or a saddle point. And so I was going to make a comment, but I will save it for later. So this is a two-variable version of the second derivative test. Where basically, if you remember in functions of a single variable, if you had a critical point, by the sign of the second derivative, you could distinguish if it was a local maximum or local minima, or if there was not enough information yet to determine that. So the statement is the following. Let f of xy be a function of two variables x and y whose partial derivatives. And now you have to think, well, you have the first partials, fx, fy, but if you have second partials, you'll have fxx, fyy, and fxy. Here we're in the case where the mixed partials coincide. So if I would know in that case that fxy is equal to fyx, so I only need to consider this. And all of them exist. And I will define a function d of xy to be the function which is below. D of xy is equal to fxx evaluated at xy, fyy evaluated at xy, minus the squared of fxy evaluated at xy. Okay, before I make an observation, what does this look like? You have some symmetry, right? Xx, xy, xy squared. So maybe it's not so obvious, but this is equal actually to the determinant of a matrix, which is fxx evaluated at xy. Then you would have fyy in this corner. Here you have fxy over here, and then fyx over here. Knowing that these two are equal, if I compute the determinant, I get this stuff. That is the only observation I will make regarding this to the case. There is way more behind, which is essentially that in 2D, the functions are approximated by planes. A critical point means that you have a horizontal plane, and therefore when you make the calculation of something called the Taylor series, the first term would vanish, and this matrix is related to the second order approximation, and that's why that stuff appears. If you have, who has seen matrices? Okay. So actually what this is related to when we will study the sign of D is basically to study if the matrix is something called positive definite. So I will not present the theory, I just want you to see that there is some math behind it and it's not magic, essentially. So that's why, because if I do not state this, then I think the criteria will be more obscure into why you care about the signs of this function. So you have several steps to follow, which are related to evaluating the sign of this object. And the first one is, of course, to find all the critical points of f of xy, as you did in 1D, meaning all points a, b, such that the partial with respect to x at a, b is equal to 0, and also the partial with respect to y at a, b vanishes. So the second step is that for each critical point a comma b that we found in the previous step, we evaluate d at the point, so d of a, right? Now, here is where the sign will be important. The same way some sign was helpful in functions of a single variable. So if d evaluated at a comma b is less than 0, there is a saddle point at a comma b. Step 4 is another case. If d evaluated at the point a comma b is greater than 0, well, so you have to wait. I mean, there will be a relative extremum, but in order to figure out if it's a maximum or a minimum, you have to compute another sign. So you would compute the second derivative fxx at ab. Now, if the second derivative fxx at ab is greater than 0, there is a relative minimum at the point a comma b. And if f(x(x) at a comma b is less than 0, there is a relative maximum at a comma b. So, and well, actually, if you think about it, both cases, which would be related to this, is that you have relative extreme. Well, actually, the convention would be here, sorry. So either a maximum or minimum when this condition happens. So you need the sign to be positive for D, and then either positive or negative for this. Now, what happens if D evaluated at a comma b is equal to 0? In that case, the test is inconclusive in the sense that f may have either a relative extremum or a saddle point at a comma b. So, well, this is a more general version of the criteria that you saw in 1D. Just to imprint some logic. Well, you think about it, the sign of that D is related to the sign of that determinant, which is related to an approximation of a given order of the function. And if you can define something that is positive with f even it or not, you can basically guarantee locally that the function is a maximum or a minimum. That's why the sign being positive is important. If it's not positive definite, for example, when the case that D is negative, you cannot make them. And you can have the case of the saddle. Now, the point is that we are approximating functions by planes. And once we guarantee the satisfaction of this criteria, when we say that there is a relative minimum for the functions that are well behaved or not, it means that it's a minimum in all directions, not only in the direction of x, but also in the direction of y, and likewise over here. But let's make an observation before we proceed. So if D evaluated at the point a comma b is greater than 0, we can restrict to a given direction. For example, the x direction, which is what we did actually when we stated this criteria. And use the sign of the second partial, f(x(x), as in single variable second derivative test. So I want you to think of what we did. If we had this negative, we have a sign. If this is positive, we need to do some evaluation. If we check the sign, if this is positive, there's a relative minimum, and if this is negative, then there is a relative maximum. However, think about it. This is a sign related to all the second partials, second order partials. Whereas this one, it's basically just along the x direction. It is because when you have a minimum or a maximum, it is in all directions. So basically what you're doing over here is to do a cut along one direction and to see if there is the minimum or the maximum in the curve that you obtain. That's why you can basically just, having satisfied this criteria of D greater than 0, to check only f(x(x). This is actually the function that would appear when you do the second derivative criteria in 1D. You would have f double prime. So after you have done this, you basically go make a cut where you consider x the only variable, and then you evaluate f(x(x). There is a summary of the signs that you might be interested in, which is also in the book, which is basically to let you quickly verify, which is, okay, you have the sign of D, sine of fxx, and then behavior at the point a comma b. So, okay, when you have it positive, and then if it is positive, then that means that you have a relative minimum. If it's positive and this is negative, this is a relative maximum. If it is negative, you already know beforehand that you have a saddle point and you do not need to evaluate this stuff. I mean, if it helps you, basically just think of the function y equal to x squared. And then you can figure out the signs of f double x, right? F prime 2x, f double prime 2. Okay? And for a parabola yx squared, you have a local minimum at 0, and for the minus x squared, you have the other. And, well, of course, to mention that the proof is beyond the course, or beyond the scope of the course. So, but I have been telling you with this, actually this matrix has a name. This is called the Hessian Matrix. And all this iteration of the plane and the approximations and the second order blah, 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 is the way you would start to think about the proof. But this is not material of the course. In fact, this expression of the determinant is not even in the textbook. So I'm just trying to help you to make more connections, not because I'm going to test you about it. So hopefully it will help you to learn better about the topic. Before we leave, we will make one last example, which is related to a simple function. Actually, before we do any calculation, we can realize which kind of relative or critical point we have. So the statement is to find all critical points for the function f of xy equal to x squared plus y squared, and then to classify. So before we do any calculation, what is this as a surface? I will help you. What is this if you think about it only as a function of one variable? It's a parabola, right? Then we saw the surfaces of revolution, where basically we rotate around the z-axis, and we make a transformation where you go from x to the square root of x squared plus y squared. So this is basically a surface of revolution from a parabola. This is a paraboloid. From a parabola, you know that you have a single local minimum. The paraboloid, which is going to be the surface of revolution, is also going to have that property. So, I mean, if you think about it, if I want to evaluate the critical points, I'm probably only going to get the origin, and it should be a local minimum. It will actually be the global minimum. Moreover, because you can think about this as the norm. So the norm is only 0 at the origin, and for all points, or the squared of the norm, the square, norm squared, and for all other points is greater. So it clearly there is a minimum, which is not only local, but actually global for this function at the origin. So now let's do the math to verify all this. But it's good to do this case because we can imagine and we can also know what happens before we actually do the calculations. So fx is equal to 2x, fy is equal to 2y. That means that if you think about the critical point, which is the points where this vanishes, it means that you have only the origin. That's the only way it can happen. Now, f double x is equal to 2, f double y is equal to 2. If you think about it, fxy, which is equal to fyx, you have no dependence, so this is 0. Now, what is the second order, well, second partials test? You would have to compute this function, d of xy, fxx times fyy minus fxy squared. This vanishes actually. So you have 4. And then this is for all xy. So the condition was that this would be positive, right? Which is what is happening. So in particular, if I evaluate at the origin, this is 4, which is greater than 0. So I only have to figure out, in terms of the computations, if this is a local minimum or a local maximum. It will actually be a minimum, since we know the figure. So we have a relative extremum at the origin. Now, what we know is that fxx is, well, is equal to 2, which is greater than 0. And so that means that there is a relative minimum at the origin. And again, just intuition, the surface, which is x squared plus y squared, is a paraboloid. Well, I could do the surface of revolution. I think that picture will be clearer, which is basically that I have the parabola, and then I rotate. So sorry for the crappy drawing, but this would be this surface. And if you think about it, this is when you make a transformation, when you obtain surface of revolution.